a two-space tab.
Oh, okay.
And it was literally two spaces.
Yeah, yeah. Yeah, tab is actually a different character as ASCII character 8.
Okay, I'll just type
Character
in
9, sorry.
8.
9. Control I.
What was the command to get an input, like a number, into FGETs when you're GUV? You know what I'm saying?
Oh, if you say next before a call to FGETs, it'll run FGETs and it'll wait for you to type in something.
Oh, okay.
Yeah, but you got to use next instead of step.
Oh.
All right, so I forgot to record the A section, so this is the only recording for today. So if your friends are looking for their recording, tell them to watch this one. All right, so welcome back from a 3-day break. Questions on PA1? So I tried to download people's repos this morning, and I only had 21 hits. So more than half the people taking this course have not created a GitLab repo that I have access to yet for linked list 1. So do that before Thursday, right? Because it doesn't always go exactly as you'd like it to go. And Thursday night, you're done, you worked on your code for 2 weeks, you're ready to turn it in, and you can't get the repo created, or you can't set me up as a reporter, or it's complaining about things being out of sync and stuff like that, right? Make those discoveries like on a Tuesday instead of like right before the deadline. So make sure you've got things set up on GitLab. I know a few people who have lost their code through various mishaps and were able to just pull it back from Git and continue on their way. So it's nice to have the backup there if something happens to your code. It's also nice to have a good Git repository when you get to looking for internships or jobs or things like that, and people want to see a portfolio of your work. You can point them to your Git repository, and they can access it from their machine and look at your code and things like that. And I've known a number of people who, 2-3 years after doing this sequence of courses are looking for a job, and the employer wants a portfolio, and now they're on Git trying to remember what they did 3 years ago in this course or in 223 and what this project was and where they put that file and that kind of stuff. It's all in there, but it's the big closet that you never look at. So if you organize this stuff as you go, if you make decent readmes, if you put some organization in your directory structure and so on, you can have this stuff available for you down the road if you want to make it available as part of a portfolio. It's a pretty easy way to repurpose work you've already done. So it's not just an annoying thing you have to do because PA1 says put it on Git, right? There's other reasons to do it too. All right, so PA1 questions? And you have until Friday to turn in PA1, but we're switching to PA2. Okay, we're going to start looking at linked lists differently today. We're going to start working with linked lists in dynamic memory, okay, which is where all of our data structures are going to exist going forward. So we've been doing linked lists for about 2 weeks, and we've been doing them with an array of struct nodes and valid flags and that kind of thing, but I want to sort of forget about those details and think about what is a linked list kind of more abstractly. And it's basically a way to store information. Well, an array is also a way to store information. We can make an array of integers, we can store a bunch of integers. When we store things in an array, we have to know where the first thing is stored. We can't just make an array of integers and forget where the array is in memory. We got to know how to get to the first thing. Okay? When we say integer x bracket 100, the value of x is the address of the first thing in the array. So we always have a way to get to the beginning. If we know where the first thing in the array is stored, how do we find the second thing in the array? Where is it stored relative to the first?
Hopefully in the first.
Hopefully like right after the first, right? If you have an array of integers, and element 0 is stored right here, element 1 is right there, and element 2 comes right after that. And where's element 3? It's right after element 2. So if this is an array of integers, and each integer is 4 bytes, whatever the address of this element is, if you add 4, that's the address of the next element. If you add another 4, that's the address of the next element. If you add 40, that's the address of the element 10 after that. So with an array, we can find any element by just saying what's the index of that, multiply by 4, add that to the address of the first. So really an array, all we need is the address of this first piece, and then everything else is just relative to that. Okay, a linked list, we break that. A linked list, we have one piece of data, and here's another one, and here's another one, and here's another one. And maybe this is our first, second, third, and fourth. And they're scattered all over the place, right? So we can't just say, well, let's just look at the next spot in memory for the next node, because it's not in the next spot. It's like way down here. So each of these things, we also have something that points to the next node. Right? That's the structure we've been building. Now we've been doing it with an array of struct nodes, but generically what we're basically doing is we're storing information. So a way to store information, and with each piece of info, we also store the location of the next piece of information. So that's what these arrows are, these pointers from one node to another. So our nodes are going to look like this. There's going to be a piece of data, and then there's a pointer to the next node. All right, so we're still going to have struct nodes. Okay, these boxes are a new type of variable. They need to have two things associated with them: a piece of data or information and some kind of pointer to the next box. So it's a more complex variable. It's a structure. So struct node. And we're going to stick with integers, but we can make a linked list of characters, strings, anything, right? We're just going to stick with integers for now. So struct node consists of a piece of data, which is an integer, and then a field called next. And next should somehow reference another struct node. So it's going to be a struct node pointer. All right, so this can feel a little strange. And if we didn't have this asterisk here, the compiler would lose its mind, because we'd be saying a struct node contains a piece of data and a struct node. Well, what's a struct node? Well, it's a piece of data and a struct node, and you get this rabbit hole, and the compiler will be unhappy about that. But that's not what we're saying here. We're saying it's a piece of data, which is an int, and it's a field called next, which is a pointer. It happens to point to a struct node, but that doesn't really matter. A pointer is basically a pointer. So that's what our struct node is going to look like. And it's fundamentally different from PA1 struct node, which was a triple of integers. So that's one big change for PA2, where struct node changes. right, so there's a struct node. It's a piece of data and it's a pointer. And every data structure we make is going to be made up of nodes that look something like this. With a tree, we'll have a pair of pointers. With a stack, it'll look just like this, or a queue. And the real magic here is this struct node star, this field that points to another struct. And it points to another struct node. It could actually point to itself. We can make circular lists where the end of the list points back to the beginning. We can make a list where something points to the middle of the list if we want. That's how we're going to get to trees. And it doesn't really matter at this level of code. Okay, I want to introduce a type def, because everything that we make pretty much is going to be a struct node star, struct node star. Struct node star is going to get old. It's going to look weird. I'm going to make a type def for a struct node star. I'll put the star next to it. I'm going to make this type def called a linked list. So anytime I say linked list, think struct node star. Okay, it's just a synonym for pointer to a struct node. All right, what should we call our linked list? I called it haha last time, so I don't want to call it haha. Haha. No, that's hard to say.
Spaghetti.
Spaghetti, okay. That's somehow easier to say. All right. So spaghetti is the name of my linked list. I don't want to call it list or node or sentinel or something like that, because I don't want you to think that that's like somehow significant. So that's the list. But what it is a pointer to a struct node. Now we're still going to use sentinel nodes. So an empty linked list is going to look like this. It's going to be one node with maybe a magic value in the data field, and a next field that's going to be a flag saying it's not actually pointing anywhere. We're going to use the word null instead of my null, because null is built in to the system. It's defined in standard I/O. So a sentinel node of an empty list looks like this.
So if we didn't want to include all of standard I/O, what would we define null as?
I wouldn't.
Star zero?
It's a void star 0, but that's only today on this system. So I would get it from somewhere else. But yeah, it's pretty much always 0. All right, so what do we do with a linked list? We want to initialize it, right? We want to create an empty linked list, which means we want to make a sentinel node and point to it. And we're going to make a function called init. Doesn't take any arguments, and it returns a linked list. So in PA1, things like this would say spaghetti is an index into our array. In PA2, spaghetti is a memory location. But if you think of memory as a big, long array containing 16 billion entries, then we're really kind of doing the same thing as PA1. The value of spaghetti, it's a pointer, but it's really just an index into this array that starts with 0 and holds memory location 0, and entry 1 holds memory location 1, and so on. Right? In some sense, pointers are just indexes into this big, long, memory-sized array. But we'll think of it as a pointer to the sentinel node.
So you're just initializing a pointer, and then you're putting stuff into it.
So I'm creating a new node which is a sentinel. I'm initializing the data value and the next value of that, and then I'm returning the address of that node, and that's what spaghetti is getting set equal to.
Okay.
So let's write the init function before we mess with it too much. All right, so init wants to create a sentinel node, wants to set the next field to null. We'll go ahead and set the data field to 42 or something, and then we'll return the address. Okay. Okay, this is not going to work. This kind of makes logical sense, right? I have a struct node I'm calling sentinel. I set the data to 42. I set the next field to null, and I return its address. And if you do this, it may work for a while. But it's not right. The problem with this is sentinel is a local variable. It's defined inside this function init, and once you exit init, that variable can get reused by other code. So you return and it looks like it's working fine, and then you call print, and print uses the same area of memory where sentinel was stored, and now your sentinel node looks totally wacky. So you might say, oh, okay, well, no problem. I'm just going to go ahead and make this global. All right, so now that is statically defined. It's not bound to init. Once I set sentinel data equal to 42, that value will persist. Right? Once I set next to null, that value will persist. This is also not what you want to do. Because if I decide my main program wants to have 5 linked lists, list 1, 2, 3, 4, 5, and I call init 5 times and set list 1, 2, 3, 4, 5 equal to init, each of them is pointing to the same sentinel node. I don't have 5 lists, I have 5 references to 1 list. Okay, if sentinel is declared like this as a global, every time I call init, it returns the address of this variable. So if I say spaghetti equals init and sauce equals init, spaghetti and sauce are both the same value. I don't have 2 lists. So what we want when we call init is we want to actually create a new sentinel node, one that doesn't already exist. We want to initialize the fields in that and then return the address of that node. And then if I call init again, I want to create another sentinel node. Set that up, return the address of that. So this is what I mean by dynamic memory. And this is declaring sentinel at compile time. It's telling the compiler, find a location for this struct node called sentinel, and it's fixed once and for all. So what we're going to do is we're going to make a pointer to a struct node. Let me leave that the way it was. Okay, so that's not what you want to do. Okay, so we're going to make a pointer to a struct node. Or I could have just said linked list, because that's struct node star. All right, well, it's declared to be a pointer to a struct node, but if I try to use the thing that sentinel points to, I'm going to segfault. right? If I don't say sentinel equals something, it probably equals 0. And when I say star sentinel, I get a sig fault. So we have to set it equal to something, some location in memory that's not currently in use, and that's big enough to store a struct node. So how in the world do we find a chunk of memory that's big enough to hold a struct node and is not currently in use?
Malloc Size.
Malloc, right? And this you either know or you don't know. I think it's touched on in 121, but not very deeply probably. So we need to use Malloc. So Malloc takes an integer which says how many bytes do we want, and it returns a pointer. So this is a location of first allocated byte. So if I say Malloc 4, the system will look for 4 bytes in memory one after another. When it finds that, it will mark it as being in use and it will return the address of that first byte. And then you're more or less guaranteed that anybody else who tries to find memory will not pick up those 4 bytes. They're reserved for me now. So if you're going to use Malloc, you need to include standard lib.h.
Got an extra greater than.
I wonder how badly that would freak out the compiler. All right, so let's call Malloc 4, and let's see what it returns. It's returning a pointer. I'm going to print it out as a %d. The compiler will warn me about that, but I'm just playing right now. So let's see what Malloc returns. So it returns 3,473,648. Maybe off by 10. All right, if you run it again, you get a different value. And sometimes you get wildly different values. So it's kind of more or less randomish.
So when you run that, where does it start to look?
So there's a piece of the system called the heap. It's a data structure we'll learn about later. Well, a different kind of heap. It's a data structure that basically keeps track of all the available memory. And when you call Malloc, it basically interacts with this data structure and says, hey, I'm looking for a chunk of memory this big. And from that structure, it can find it.
Okay, so it just starts at the beginning of it. It just keeps going.
I don't know what the exact algorithm is. You can download the source code. It's probably a few layers deep. And allocating memory is a pretty expensive operation. It's a pretty frequent operation, so there's probably things they do to try to optimize that. So let's call Malloc a bunch of times in a row. And the numbers are not quite random.
Pretty close to each other.
Pretty close to each other.
But they're greater. So it looks like it is kind of linear.
Yeah, they're increasing.
They're all even.
And they're always even.
Isn't there a reason for the always even thing?
Oh yeah. They're actually always divisible by 4, possibly by 8. What else do you see?
It's increasing by 32.
32, right? I wanted 4 bytes. It gave me enough space for 32. Or at least it skipped over the next 28 bytes and then it gave me an address that was 32 beyond the previous address. So there's a chunk size to Malloc. If I only want 4 bytes and it gave me 35, 205, 136, the next time I called Malloc, it could have given me from location 140, and the next one 144. But that's not efficient. So there's a place where software and hardware meet. Okay, this is one of those places. because memory, we think of it as just a big collection of bytes, right? But it's really not. It's organized in structures. So physical memory is usually like 32, at least 32 bits across, often more. The various pieces of memory management system, if you've done Engineering 270, cache memory, virtual memory, all that kind of stuff, that's all tying into here. And allocating on these 32 byte borders increases efficiency. So I asked for 4 bytes, well 28 bytes are kind of wasted now. That's just how it goes.
So what happens if you asked for more bytes than the heap had? What would it return?
Oh, we'll get there next.
Okay.
So let's ask for 33 bytes. So what is it increasing by here? 48. So it's more like a block size of 16, but a minimum of 32. We don't care about these details, right? These are totally like irrelevant to us.
These are engineering details.
Yeah, these are engineering details, but they're interesting to see. And as you're working with this stuff, and I've warned you, we're going to be using the debugger and examining memory at a very low level, you're going to be exposed to these kinds of things, right? So you'll see things like this and wonder sometimes. All right, so let's allocate a bunch of memory. And it returns a 0.
Does it return a 0 or a null pointer?
Well, that's an engineering detail too. It's always returning a pointer, but the value of that pointer is 0. So let's look at the value of null. Null is a 0.
So it probably just returns null.
And if you really want to do this right, you can do a %p for a pointer. And then you don't get those warnings, and you get nil. So it knows that if you're trying to print out a pointer and it's equal to 0, that's basically null, which is also called nil. Did you have a question? Did you have? Okay. So if you try to get too much memory, it'll give you back null. And that's your flag saying, okay, that's not the location I should be using for my struct node. That's a flag I should pick up and say, hey, we're out of memory. Okay, is this ringing any bells? Right, so this was PA1. We used my_null instead of null because we didn't want to use 0, we wanted to use -1. But PA2, we're just going to use null, N-U-L-L, uppercase. It's already defined for us as 0, so we don't have to set it up ourselves. It's defined in standard io.h.
To make it simple, could we just set my_null equal to null instead of -1?
Nah, because you got to start using null at some point anyway. So PA2 is a good place for it. And it keeps your code portable in case like they change
We've already
null
got it
on
all
us.
defined.
I know. You could define my_null to be null though.
That's what I meant.
Yeah, okay. Yeah, you could do that. But it looks cooler with null. Alright, so back to our initialization. So Sentinel is going to be a pointer to a struct node. We need to get this memory at runtime. I'm spelling Sentinel funny. So we're going to call Malloc. Okay, and say give us some dynamic memory. So how much memory do we need to store a struct node?
An integer plus a pointer.
An integer plus a pointer. So our struct node is an int followed by a pointer. Well, we probably know that an int takes 4 bytes.
On some.
On some. On the server, a pointer takes 4 bytes. On my laptop, a pointer takes 8 bytes. So we don't want to calculate this ourselves. So there's a built-in function in C, well, built-in keyword called Sizeof. And Sizeof lets you specify a type of variable, and it will tell you how many bytes you need for that type of variable. Okay, so this is one of those really, really important things I'm about to say. This will save you potentially quite a few hours. So what you put in the argument to Sizeof is a type of variable, never the name of a variable. Don't say size of I. If I is an integer, say size of int, int. If you have a struct node sentinel, don't say size of sentinel, say size of struct node. Okay? This is really important because if you use the name of a variable, usually it will work. Once in a while it won't. In most cases, the name of the variable will work just as well as the type of variable, but not always. And when it doesn't work, it won't blow up right away. It will allocate too little memory, and it will set up a little time bomb, and 500 lines later in your program, you'll suddenly segfault. And it'll be, you know, in a totally different function in another file where you did size of sentinel instead of size of struct node. And it's really hard to find these. Okay, so the easiest way to avoid that is just never use the name of a variable. Always use the type of a variable. All right, I should make a T-shirt for like whoever doesn't do this first. It'll be a consolation prize. All right, so so the type of variable that we're trying to create is a sentinel. What is a sentinel? It's a struct node star. Okay, but we don't want a malloc size of struct node star.
Because that's a pointer.
Because that's a pointer. What we're trying to do is create a chunk of memory that can hold a struct node. We're going to assign it to sentinel, which is a pointer, but a pointer is always 8 bytes. Doesn't matter what it's pointing to. I could have a structure that takes 1,000 bytes of storage. I would want malloc to give me 1,000 bytes. But if I malloc struct node star, it's only going to give me 8 bytes. So what I really want here is, in this case, the size of a struct node. And if I said size of sentinel, it would give me 8 bytes. And that's not enough for my struct node. Now it actually gives me 32, so that's not going to blow up. It's only allocating 8 bytes, but it's going to give me some buffer in there, right? But if I needed 1,000 bytes and it only gives me 32, that's going to be one of those things that'll blow up eventually. All right, so malloc size of struct node. That is a new struct node.
Is there any specific reason you weren't putting it on the same line as you initializing it?
Nope, you can do that. All right, so we want to set the data field to 42. So sentinel is a pointer to a struct node. I gotta keep spelling it wrong. So star sentinel is a struct node. Sentinel is a pointer to a struct node. Star sentinel is the actual node itself. So I can say something like this.
Or can we use arrow?
Or we're going to use arrow, which we're going to in a minute. So this will initialize the 2 fields in my sentinel node. And then what should I return?
Just sentinel.
just Sentinel, because Sentinel is a pointer to a struct node. This making sense? Yeah.
So I know you said that in Sizeof you can't put in an actual variable, but a type.
Mm-hmm.
So could putting in linked list instead of struct node work as well, because we didn't predefine it?
Yeah, except that linked list is a struct node star.
Oh.
So that's the one kind of inconsistency.
But if you were trying to malloc a pointer, then yeah, you could.
Yeah, yeah.
Okay.
All right, so this should create, this should get a chunk of memory that can hold a struct node, set the two fields of the struct node to 42 and null, return the address of that. And up here in our main program, when we say spaghetti equals init, spaghetti should be the address of that struct node. So let's just print out the data field when we get back to the top. So don't forget to prototype your functions. And I got some other issues too.
You forgot to define it.
How's that look? Happiness. All right. So if we run that, it'll tell us spaghetti's data is 42. All right. So I want to dig further into this. So, couple of details. This is correct, right? Take the thing that Sentinel points to. That's a struct node. Give me the data field. Okay, but it's cumbersome. It's not bad like this, but sometimes what we're going to do is say, take the thing that Sentinel points to, give me the next field. Now take the thing that that points to, and give me the next field of that. And now use that as a pointer, take the thing that that points to, and give me the data field of that. And it's going to be a bunch of nested parentheses with asterisks, and it's really, really cumbersome to read. So there's a different way to write these two statements. So we can write Sentinel and then this arrow, which is a dash followed by a greater than sign, so it looks like an arrow. If we say Sentinel arrow data, that's the same as star Sentinel dot data. Okay, it means the thing the Sentinel points to is a structure. So take the structure that Sentinel points to, that's the arrow part, and give me the data field. And in this case, set it equal to 42. Okay, and Sentinel arrow next equals null. Same idea. So let me get rid of this will not work code.
If you have a structure inside of a structure, so say data was another structure, could you do
You can
Sentinel?
keep chaining the arrows. Yep. So same thing up here. I can just do spaghetti arrow data. Now, if you want to think of it like this while you're working on this stuff, you can come back to this idea. But we really want to be writing it like this, right? Almost never will somebody actually write this, except when they're trying to figure out what the arrows are all about and what these pointers to structures are. But you'll almost never see this actually written in code anywhere.
So does the arrow actually get turned into that, literally, or is it a different operation?
That's a good question. I don't know what happens in the compiler.
Like, would it be more, like, for example, like speed efficient, or
I'm
memory
pretty sure
efficient?
they'll compile exactly the same way. What I don't know is if the compiler actually changes that arrow into this. I'm guessing it probably does. I mean, that's the operation it's performing, so. But I don't know if it actually, like, makes a buffer that corresponds to that. But yeah, they should be identical in compiled form as far as I know. Alright, so this should work just fine. Right, exactly the same thing. So let's compile with GDB. Let's go into GDB. And let's just step a few times. And let's look at spaghetti. Spaghetti is hex 602010. It's a memory address. I can use X to examine memory. So if I look at that location in memory, I find the hex number 2A. What's 2A? 2 times 16 plus 10, that's 42. That's our data field. And this is our next field, but it's just zeros, null is 0. So we can't really tell that. But that's where the data field gets stored. But we can play with this. Let's set the next field equal to hex 1, 2, 3, 4, 5, 6, 7, 8. Don't do this unless you want a seg fault. See, it knows I'm going to get in trouble. But if we look at spaghetti, it's hex 602010. If we look there, there's our 42. There's a bunch of zeros. There's a 1, 2, 3, 4, 5, 6, 7, 8. So somewhere in that area after the data field is the next field. And to some degree, we don't care about this. To some degree, all we care about is, you know, the C code. But when we're debugging, we're going to have to go into GDB. We're going to have to look at memory and deal with things at a low level and see where things are actually stored and what's pointing to what. We'll have an exercise we can do in class later this week to mess around with that. All right, let's talk about the ODP. So this opened up over the weekend. It's due tomorrow morning. Going forward, the ODPs, I'm posting the READMEs on the server. Okay, they're posted for the next 7 ODPs, but you can only do ODP 205 until tomorrow morning. So you can read the README for 206, but if you write the code and try to assess it, you'll get a 0 probably, because this is the ODP that's live. So you got to look at Canvas to know which ODP you're supposed to be doing. And if you try to do 206 and you get a 0, make sure you go back and reassess 205 so you get your 100% on it. Because whatever the last grade is that's recorded, that's the one you get. Okay, so ODP 205, this is kind of a hello world for playing with structures and dynamic memory. So define a struct node as shown, integer data, struct node next. Okay, that's what we've been playing with. And you're writing a function named set. The prototype for set is as follows. It takes a struct node star, it doesn't return anything. And the only thing that set does is you pass it a pointer to a struct node. Okay, you can assume that struct node is, you know, an actual node stored in memory somewhere. Find the data value, multiply it by 2, store that in the structure. Take the next field, set it to null. And then just return. So set, you pass it a struct node. When set returns, the data field of that node should have been doubled, and the next field should have been set to null. So you're not doing any calls to malloc. You're being given a struct node, right, a pointer to it. You're not doing any mallocs, you're not doing any ifs, you're not doing any loops, scanfs, gets, prints, none of that. Okay? It's basically two assignment statements. Set the data equal to twice what it is, set the next field equal to null. So if you understand the idea of a pointer to a struct node, this is, you know, one line of code other than defining the structure. And it might take you a few minutes to write. But if you don't understand quite exactly what a pointer to a struct node is, or what a structure is, or what a pointer is, right, this will take longer. And will take as long as it takes to figure out more clearly what a pointer is, what a structure is, that kind of stuff, right? It's time you want to spend on exactly that.
In worst case scenario, you can ask the Discord.
And you can ask Discord, right? Or you can ask me. So this can be really frustrating because it's so simple, seemingly, right? There's just not a lot of, you know, if you write 1,000 lines of code and it doesn't work, that's great because you got so many things you can change, right? This is like such a rarefied assignment that if it doesn't work, it's kind of like, well, I have no idea what to do because this is the only way I can imagine doing it, right? So so try not to push that away. Try to actually like take that as an opportunity to say, okay, so what is this struct node star next, right? And ask questions. Shoot me emails. Ask questions in Discord. If you ping me in Discord, put my name on. But you know, give yourself some time to figure this out, because this is the building block for everything else we're going to do in data structures. Basically pointers to structs. That's what we're going to do for lists, trees, queues, heaps, stacks, everything else, right? So this is time well spent figuring this out. Write your function, write some test code, right? Make a struct node that's not a pointer. Make an actual struct node. Pass the address, give the data field something, give the next field something. Pass the address to set, and then print out the data field in the next field after you get back from set. Data should be doubled, next should be 0. Right? And then once it's working, go ahead and link in with the test bed and do the usual assessment. Make sense? All right, rock on. I will see you tomorrow. We'll start talking about PA2 tomorrow in the next ODP.